All right, here we go. Stats, 3.5 notes, descriptive measures for population, use of samples. Goal 1, calculate the measures of measures of center for population, and then distinguish between the use of measures of center for sample versus population. Example 1, we just practiced that using all these different samples of 25 runners, entering them into Google Sheets, and it says we're going to fill in X bar and S. Whatever you calculated, you can fill in on those lines. Evan, what did you calculate for X bar for your set of 25 runners? So 241, and what did you get for your standard deviation? 40. Excellent.
So your X bar is your mean.
X bar is your mean. Whatever you calculated, and if you didn't get yours finished, then you can just put these in, that's fine. And then it says, click here. If you don't believe me, you can click here, and you can access the spreadsheet. I'm going to do this real quick. I'm going to pull up the spreadsheet. This is all the runners, all the data. And you can see here 246.51, so I'm going to round that to 247 with a standard deviation of 45. So I'm going to fill those in, 247 and 45 for all 947 runners.
What should I, wait, so, what's that calculation? What should I put?
You just calculated yours for 20. You should, if you used Google Sheets, it automatically did those calculations for you. Remember, for mean, we use equals average. And then for standard deviation, I think most of you remember that one, equals STDEV, and then whatever those values are. Makes life a lot easier to let Math Excel or Google Sheets do the work for you. When we compare these values, 241 is pretty close to 247 when you think about 947 runners being represented by just 25 runners, a sample of 25. The standard deviation is a little bit bigger, but again, those are pretty close. We use sample statistics to make estimates about the population. Here's a table that we're going to write, kind of collect all of the things in comparison. First of all, the sample, remember, is a lowercase n. Well, that's a letter that we use for the sample size. For the population size, we use uppercase letter n. Very similar. So these are the ones for the whole population. So everyone should have the same thing here and here. You're good, you're good. Good question. The mean, we know for sample is X bar. So if you forgot what that is, here's a table for reference. And I know you were just hoping, last lesson of the chapter, for a couple more Greek letters, and I will deliver. We have a couple new Greek letters today. Get excited. One of them is the Greek letter M, pronounced U with an M in front. Mu.
Oh, that's cute.
Standard deviation, we already know, is the lowercase letter s. Little Greek. Lowercase letter sigma. It's like a little oval with a little horizontal line at the top.
So it's like
Like a pumpkin, but like a
person as well.
Yeah, kind of like a little lemon or little pumpkin or whatever you want to think of it as. The terminology then for a sample when we're talking about these measures is statistic. We call those statistics. And for population, the terminology is a parameter. Parameter.
Okay.
the standard deviation of the population. And now you have space for 2 of your 3, so go ahead and just cut them all out real quick. Cut these beads out. Oh. There's 3 things to cut out. There's the little formula, there's you did the thing, Bitmoji, and there's the Z-score rectangle. Little formula. Thanks. These are going right here and right here. You did the thing. You already calculated. We already experienced the population standard deviation and the population mean. Well done. Glue it in. Yes. I'll give it to you. Right here. Thanks, Evan. The formula for the parameter mean, the population mean, it's the same process as we did with the sample mean. Different symbols, same process. We add them all up, and we divide by how many there are. So in Math Excel, again, this one is just equals average. It's the same formula. I just stuck it in.
We're cutting stuff out.
If you're still cutting and gluing, that's fine. I'm gonna keep on filling in some things. The population, so that they go here and here. I outlined it because it blends right in with the page. The mu formula. So this is just what we just said, but in words. The population mean is calculated in very much the same way with its own notation. And we already wrote in that new notation above. Here we're going to write it in again, a little practice for writing the Greek letter M, mu. It's pronounced mu. You already wrote that. It's a little bit repetitive. Maybe it'll stick that way.
Just write mu and then in parentheses, like the Pokemon.
So people keep telling me, yeah. N is the population size. Just like we wrote in chart form above. For any given population, there can only be one population mean. Makes sense. There's a population. There's only one way to add those all up and divide by how many there are. But with the sample means, like we did with the marathon runners, lots and lots of different ways that you could take sample means from a given population.
Wait, I guess it's
Sample. If you've got this all written down, make sure your little marathon runners are all stacked up nice and neat for me. I'll collect those in just a couple of minutes. Like I said, today goes by quick.
Yeah, we got
40 minutes goes by fast. Here we go. I'm going to flip the page. If there's something you didn't get, I have extra copies. You can get those down in just a minute. With this example, there's a lot of background information about this golf course, the Augusta National Golf Course located in Augusta, Georgia. And we're going to focus in on the length of the holes on the course. So it says For all of these golf course holes, there's a length, and we want the population mean. We want to add these all up and divide by 19. There's 19 of them. For this population, that mean is 413. As you can see, if you were using the electronic version, you could just click here. You could see my little list of all of the holes, lengths, and you could average these all together. You would get 413. Recall, now we're moving on to population standard deviation. We just talked about population mean. It's the same calculation. With population standard deviation, recall, first of all, the sample standard deviation for variable x and a sample of size n for population is represented by this formula. We don't see it all that often because we often use the shortcut method of equals stdev and then open parentheses and so on. Then below I have the population. So you can fill in population in this blank right here. Population. To distinguish the population standard deviation from the sample standard deviation, intentionally we used a different symbol. That's the sigma. So the formula difference here, does anybody spot it right away other than the difference of symbols?
What?
There's one slight difference between these two. Morgan?
Instead of like the lowercase n, it's not -1, yeah.
Okay, good. There's not a -1 in the second one. That's the only difference. There's slightly different symbols, but the n-1 is the fact that when we take a sample standard deviation, that is an estimate. Dividing by n-1 gives us a little bit of cushion. It gives us a little bit greater range in which to estimate our 68, 95, and 99.7% of the data. So it all kind of ties back into this empirical rule right here. So the population variance for the variable is represented by sigma squared. Just like the sample variation variance was represented by s squared, lowercase s. Back to our golf course example. We've got, don't worry though, because there's this formula, right?
Oh, yeah.
It's different though. There's a dot P. That's the only difference. This one up here for sample, if it helps you, you can use a dot S for sample, but you don't need it. stdev, and then we put our first and our last values in there. But if it's for a population, we have to include the dot P. And that lets the sheets know, hey, divide by just n instead of n-1. So example 2 says, not surprising, we're going to calculate this population standard deviation for the lengths of the holes on the golf course. And when we calculate that, it's 132. So again, on this sheet, these are all the lengths of the holes, and I'm going to type in that slightly adjusted formula into that bottom cell equals stdev.p, and then A2 to A19. And then this little note below that says, just as the sample mean can be used to estimate the population mean, the sample standard deviation can be used to estimate the population standard deviation. A little review of our parameter versus statistic. A parameter is a descriptive measure for a, who remembers from the front? Population, good. We got a little alliteration there. Parameter, population. Statistic is a descriptive measure for a sample, good. So again, putting it into sentence form, note that mu and sigma are parameters, while x bar and s are statistics.
What do you mean by parameter? Like,
It's just the terminology that we use when we're referencing measures.
so it means the exact same thing as just like statistics, it's just for population.
Yep.
What does that mean? No, wait, I'm just confused.
So if I'm saying like the parameter for the variable of marathon time, the parameter is going to be referencing anything having to do with the entire population. So the population mean, or the population standard deviation, or the population size parameters. Those are all parameters. But if I'm talking about the statistics of the marathon runner times, that would just be having to do with each individual sample. The sample mean, the sample size, the sample standard deviation. This is it. Last topic, last new letter. It's, don't worry, it's English. It's Z, the English letter Z. And it's the standardized version of the variable x.
Where did you write the, oh, it's right there.
Now, these little bulleted point sentences that are so impactful. The standardized variable always has a mean of 0 and a standard deviation of 1.
Okay. So, hold on, what does that mean?
So if you took the empirical rule and you drew a little curve, like bell-shaped curve, the middle is always going to be 0 for the standardized variable x. And instead of doing plus s, I just go up 1, 2, and 3. So plugging things into this formula is going to make all of my observations fit into this diagram. And we'll look at an example, so it'll start to make more sense.
So like you can take, like for example, the golf course then, and you just convert all the values into a system of like 1, 2, 3.
Yeah. And it really, really clarifies how far those are from the mean, when we're only dealing with -1, -2.
So 0 is the mean. That's
0 is the mean, yep. So let's take a look at this example. We've got standardized, or determine the standardized version of x for this little data set here. We only have 6 observations, so keeping it simple. We have to rewrite this formula, but plug in the mean and the standard deviation for this population. I'm going to give those to you. You could quickly calculate the mean, add up -1, 3, 3, 3, 5, and 5, divide by 6, and you would get mu equals 3. It might take you another minute to pull out Google Sheets and enter those in, but you could pretty quickly then also get the standard deviation of this little data set here is 2. That's all I need to create the standardized variable equation here. X minus 3 divided by 2. You'll notice the x is still there. I've just replaced the mean and the standard deviation. So this is that formula that I'm going to be able to plug in any observation to make it fit onto that empirical rule standardized version from -3 to 3. Again, let's finish through this example, and it'll start to slowly make sense, and we'll practice it one more time. If x is 5, for example, just like these last two observations, if x is 5 and I plug it in to the equation here, I get 5 minus 3 divided by 2. I get -2, I'm sorry, not -2, +2 divided by 2, which is 1. So in the chart, I plug in a 1. The z-score for an observation value of 5 for this data set is 1.
So where are we? I think I'm just a little bit confused because I don't know where are we getting all these ones?
So we created this formula, which is called the standardized version, the standardized equation for x for this particular data set. I plugged in the mu and the sigma for that data set. And now I'm going to plug in each one of these values. The 5 came from the data set. I just plugged in a 5, and as promised, once I plug in any observation, it's going to land between -3 and 3 when I plug it into that formula. The next two we're going to do are -1. So for x equals -1, and for x, these are for x. So when x equals -1 in the data set,
Oh, no, sorry.
Well, I don't, so.
walk with me through the whole thing, and it'll start to make sense, and then you'll do some more practice, and if you need any help with the practice, I'm here to help. So plugging in a -1 for x, we get -1 minus 3 divided by 2, just substituting in to the equation, I get -4 divided by 2, which is just -2. I can fill that into the chart. And then for x equals 3, the z-score is, go ahead and plug in 3 for x into the formula. We're just pulling these values from the observations, the values of x in the data set,
Oh, so like,
and we're going to plug them in
that would be 0, right?
to the formula. Yep. So each one of these is going to be a 0. As promised, because we know that the mean was 3, and we have an observation with that same value as the mean, so those turn out to be 0, right, landing right there in the middle. We'll see that visually on the back of this page with the dot plot.
So what if you did that and if none of them equals 0? Like,
Then none of your observations were the exact same value as the mean.
okay, but you can still plot them right and then.
Yeah. So you would plot all of these in the context of -3 to 3. So I could plot a -2 here, and then 3 zeros, and then 2 1s. Does that make sense?
No.
So, and then on the back, we're going to go ahead and take, in just a second, we'll plug that in. You see how those two distributions look the same? One just happens to be on the scale of x, where all of the observations are kind of as is, right? Versus the standardized version on the scale of z, everything fits between -3 and 3. So my last little insert here is for z-score. I'm gonna cut that one out, paste that one in. Whenever we have a negative z-score, like we did here with the -2, notice that that value is just below the mean. That works out when we're talking about the standardized version of the variable. Whereas if I have a positive z-score, that would indicate that the observation is above the mean, like we had here with these positives. And back to the last example here, when we had the mean of 413, I'm going to round it to the nearest whole number. When we had the mean of 413 and the sigma of 132 with my golf course scenario, I can make my standardized version of that variable by just plugging in the mu and the standard deviation. So if x was 180, I could plug in 180 and I would get -1.8. I realize it's time, but I'm going to just finish up this last example so everyone has this completed set. And then I will answer all of your questions. We have lots of time this afternoon. For this last example then, when x is 495, we just plug that into the formula. So we've got 495 minus 413 divided by 132, which is 0.62. So that concludes our notes on 3.5.